Good afternoon, ladies and gentlemen. I will talk about a very small project in some sense, on-board detector or detectors for ion identification. Yeah. So I'm not expert here, but I like these figures, and I understand that this is the main motivation and general motivation. So we would like to understand the composition of the particles in the space, development in time. We would like to understand. So we have two kinds of particles or events, rays, whatsoever, solar energetic particles, and then anomalous cosmic rays, which I will not go into details of the mechanism, how it works, because you are experts there. But I would like to translate this formulation of studying of such processes in a detector language. So the translation is real-time particle identification and energy measurement. Okay. The talk is motivated by another talk, which I heard basically half a year ago during a picosecond workshop in Zurich. Why? I will tell you soon. But this is basically about the different technique, how to measure energy of the particles using new, very fast electronics. So comparison is that in old so-called delta E minus E technique, you have a thin detector, thicker detector, and you measure passing through first, second, you compare differences, and what is necessary is that the particle stops in the second detector, which is thicker usually. So here what the AGILE proposal in this project is so-called pulse-shaped discrimination technique, which works differently, and I will come to this. So the keywords are fast electronics, waveform sampling. This is what it is about. Why or how I came to this? We are working on a picosecond detector. I mean, the resolution of the picosecond. At the moment, we have a 25 picoseconds resolution in a very radiation harsh environment at LHC. You see our detector here. This is AEFP detector, Atlas Forward Proton. The proton is going through, here. So proton is going through the silicon detector, right? 4 layers of the silicon detector, entering to the bars, so-called bars, which is fused silica. And here the Cherenkov radiation is born and goes to the MCP-PMT. The full channel, and I will not go through, is shown here. But it is basically, we are getting signal via MCP-PMT, microchannel plate, photomultipliers. Then this signal is preamplified. Then we are using constant fraction discriminator. And we are using, at the moment, high-performance TDC, which is CERN product, both modified by our colleagues from Alberta. So we have some 70 picosecond roughly resolution, but now it's a pico TDC on the market, again CERN based, which has a 3 picoseconds. So this is extremely important that you can slice with such a time resolution. We as a group, and I will come to this, what means the group, we have a full experience with this detector, which means starting from mechanics, operation of the detectors in vacuum. We work several years on MCP-PMT, so we try to improve its properties in the sense that we would like to achieve stable gain even for 20 or 40 megahertz frequency, because this is a frequency at LHC. We have experiences with production of a trigger, pulsar for the testing of the module, and time to digital conversion. This is radiation hard detector. Basically, NEC is better than 5×10⁵ per square centimeter, and dose is better than 1.4 megagray. The team when I mentioned team, there is actually no real team at the moment. We are people from working with Atlas, people from Olomouc, from Pilsen, and from Faculty of Mathematics and Physics, Charles University. Here I put, specialization or the topics which different teams are working on. And we would like, based on this, what I've shown you, we would like to work on the development of two types of detectors on a satellite. The first one will be based, will have a picosecond time resolution, and this will allow us to measure really the types and energy of the particles, AGILE project. The second one is based, it's a Cherenkov kind of detector. Oh, sorry, I should say, this is not necessarily Cherenkov-based detector, of course. The AGILE is not based on Cherenkov radiation, it's a silicon detector. Here, the purely Cherenkov detector is based on the fact that the number of photons and the amplitude is scaling with z square, with a charge. So this you can use. Of course, there is a caveat that beta can be, you have to have a positive number here. Okay. So for what all this technology can be used, and this is, I think, a message which many of you gave. So it's a monitoring and protection on all possible Earth activities, which are shown here, or for the monitoring when we are going to explore the universe. Here is a list of the relevant publications from 2018, but I will not go through it. And I would like to thank you for your attention. And I would like to stress the principle, how it works is in a backup, but it's much better if you go directly to the AGILE project and you see it there. Thank you.
Thank you very much for your presentation. Are there any questions?
Thank you very much for a nice talk. I was just interested, you mentioned XTDC, that they are commercially available with resolution 3 picosecond. Could you comment on that?
Yes. PicoTDC had a delay of several years, and they are now available, for the interested groups now in CERN, link, but they were produced in some quantity. Probably they can be out of stock now. There was a big interest in it, and if there will be enough interest, they will produce them again. So I don't know if I'm answering completely. You can still try to ask CERN, for the PicoTDC, 3 picoseconds. It's tested. We had a prototype, and we have several prototypes.